Learning objectives. In this chapter, the user would learn the following aspects of graph theory: basic definitions, trees and graphs, connectivity of a graph, cut points, cycles, Hamilton graphs, trees, different characterization of trees, bipartite graphs, planar and dual graphs, Euler theorem, algorithms on graphs and trees like breadth first search and depth first search, Dijostra's algorithm for shortest path, Floyd's algorithm for all pair shortest paths, Kruskal's and Prim's algorithm for minimum cost spanning tree. Graph theory. Graph theory is a branch of mathematics concerned about how networks can be encoded and their properties measured. It has been enriched in the last decades by growing influences from studies of social and complex networks. History of graph theory. Königsberg bridge problem. The history of graph theory may be specifically traced to 1735, when the Swiss mathematician Leonhard Euler solved the Königsberg bridge problem. The Königsberg bridge problem was an old puzzle concerning the possibility of finding a path over every one of 7 bridges that span a forked river flowing past an island but without crossing any bridge twice. See the diagram. Euler argued that no such path exists. His proof involved only references to the physical arrangement of the bridges, but essentially he proved the first theorem in graph theory. What is graph theory? Branch of mathematics concerned with the networks of points connected by lines. Definition of undirected graphs given. Adjacency. Two vertices u and v are adjacent if there exists an edge uv that connects them. Incidence. An edge uv is said to be incident upon nodes u and v. Loops. An edge e equal to u, u that links a vertex to itself is known as a shelf loop or reflexive tie. Example. As an example, the graph undirected depicted in figure 5 as vertex set v equal to a, b, c, d, e, f and edge set e equal to a, b, b, c, c, d, c, e, d, e, e, f. Formal definition of graph. A graph G equal to v, e consists of v, a non-empty set of vertices or nodes, and e, a set of edges. Each edge has either one or two vertices associated with it, called its endpoints. An edge is said to connect its endpoints. The set of vertices v of a graph G may be infinite. A graph with an infinite vertex set or an infinite number of edges is called an infinite graph, and in comparison, a graph with a finite vertex set and a finite edge set is called a finite graph. Multigraphs. Graphs that may have multiple edges connecting the same vertex are called multigraphs. When there are m different edges associated to the same unordered pairs of vertices u, v, we also say that u, v is an edge of multicity m. That is, we can think of this set of edges as m different copies of an edge u, v. Example. Subgraph. A graph G1 is a subgraph of another graph G if and only if the vertex and edge sets of G1 are respectively subsets of the vertex and edge sets of G. Example. Each of the 3 graphs G1, G2 and G3 shown on the right of figure is a subgraph of the graph G on the left in this figure. The subgraphs do not have to be drawn the same way they appear in the presentation of G. Subgraph. Figure depicts a graph G and 2 subgraphs G1 and G2. The last graph in this figure, G3, is not a subgraph of G because the 2 vertices of degree 3 in G are not adjacent. Directed graph or D graph. V, E consists of a non-empty set of vertices V and a set of directed edges or arcs E. Each directed edge is associated with an ordered pair of vertices. The directed edge associated with the ordered pair U, V is said to start at U and end at V. Path graph. Informally, a path is a sequence of edges that begins at a vertex of a graph and travels from vertex to vertex along edges of the graph. As the path travels along its edges, it visits the vertices along this path, that is, the endpoints of these edges. Paths and circuits. Let n be a non-negative integer and G be an undirected graph. A path of length n from U to V in G is a sequence of n edges E1, etc. En of G such that E1 is associated with x0, x1, E2 is associated with x1, x2, and so on, with n associated with xn minus 1, xn, where x0 equal to U, xn equal to V. When the graph is simple, we denote this path by its vertex sequence x0, x1, etc. xn, because listing these vertices uniquely determines the path. The path is a circuit if it begins and ends at the same vertex and has length greater than 0. The path or circuit is said to pass through vertices x1, x2, etc. xn, or traverse the edges E1, E2, etc. En. A path or circuit is simple if it does not contain the same edge more than once. Path graph. In the simple graph shown in figure, A, D, C, F, E is a simple path of length 4 because A, D, D, C, C, F and F, E are all edges. However, D, E, C, A is not a path because E, C is not an edge. Note that B, C, F, E, B is a circuit of length 4 because B, C, C, F, F, E and E, B are edges, and this path begins and ends at B. The path A, B, E, D, A, B, which is of length 5, is not simple because it contains the edge A, B twice. Paths and circuits. Let n be a non-negative integer and G be a directed graph. A path of length n from U to V in G is a sequence of edges E1, E2, etc. En of G such that E1 is associated with x0, x1, E2 is associated with x1, x2, and so on, with En associated with xn minus 1, xn, where x0 equal to U and xn equal to V. When there are no multiple edges in the directed graph, this path is denoted by its vertex sequence x0, x1, x2, etc. xn. A path of length greater than 0 that begins and ends at the same vertex is called a circuit or cycle. A path or circuit is called a simple if it does not contain the same edge more than once. Simple graphs. Graphs in which there is no more than one edge between any two vertices and in which no edges goes from vertex to the same vertex are called simple. Degree of a vertex. Degree of a vertex in an undirected graph is the number of edges incident on it. In a directed graph, the out degree of a vertex is the number of edges leaving it, and the in degree is the number of edges entering it. Degree of vertex 2 is 3. Degree of vertex in an undirected graph is the number of edges incident on it. In a directed graph, the out degree of a vertex is the number of edges leaving it, and the in degree is the number of edges entering it. The degree of vertex 2 is 2 and the degree of vertex 4 is 1. Find the degree of the following graph. A has degree 0, B has degree 1, C has degree 2 and D has degree 3. In any graph, the sum of the degrees of the vertices equals twice the number of edges. Degree. A graph has exactly 4 vertices, each of degree 3. How many edges does this graph have? the sum of degrees of the vertices is 12. By the theorem, this number is twice the number of edges. So, the number of edges is equal to 12 by 2 equal to 6. Weighted graph. A weighted graph is a graph for which each edge has an associated weight, usually given by a weight function W. E implies R. Walk, path and cycle. Weighted graph. A walk is in sequence of nodes V1, V2, etc. VL such that V1, V2, V1, V2, etc. V1, V2. E. Example V2, V3, V6, V5, V3. A simple path is a walk with no repeated nodes. Example V1, V4, V5, V2, V3. A cycle is a walk V1, V2, etc. VL where V1 equal to VL with no other nodes repeated and L greater than 3. Example V1, V2, V5, V4, V1. A graph is called cyclic if it contains a cycle, otherwise it is called acyclic. Walk, path and cycle. The relation between walk, path and cycle is shown. Complete graph. Degree of vertex in an undirected graph is the number of edges incident on it. In a directed graph, the out degree of a vertex is the number of edges leaving it, and the degree is the number of edges entering it. A complete graph is an undirected or directed graph in which every pair of vertices is adjacent. If u, v is an edge in a graph G, we say that vertex v is adjacent to vertex u. V nodes and v star v minus 1 divide by 2 edges. 4 nodes and 4 cross 3 divide by 2 edges. Draw a complete graph with 4 vertices. A complete graph is an undirected graph or directed graph in which every pair of vertices is adjacent. If u, v is an edge in a graph G, we say that vertex v is adjacent to vertex u. Connected graph. An undirected graph is connected if you can get from any node to any other by the following a sequence of edges, or any two nodes are connected by a path. Strongly connected. A directed graph is strongly connected if there is a directed path from any node to any other node. Bipartite graph. A bipartite graph is an undirected graph G equal to v, e in which v can be partitioned into two sets v1 and v2 such that u, v belongs to E implies either u belongs to v1 and v belongs to v2, or v belongs to v1 and u belongs to v2. Map and coloring. A map is a partition of the plane into connected regions. A coloring of a simple graph is the assignment of a color to each vertex of the graph. Can we color the regions of every map using at most 4 colors so that neighboring regions have different colors? Map coloring, graph coloring. A region, a vertex. Adjacency, an edge. Scheduling and coloring. 2 committees cannot hold meetings at the same time if 2 committees have common members. Model. One committee being represented by a vertex. An edge between 2 vertices if 2 corresponding committees have common members. 2 adjacent vertices cannot receive the same color. Scheduling problem is equivalent to graph coloring problem. Incidence and adjacency. 2 vertices u and v is an undirected graph G are called adjacent or neighbors in G if u and v are endpoints of an edge E of G. Such an edge E is called incident with the vertices u and v, and E is said to connect u and v. The vertices u and v are called endpoints of the edge u, v. Strongly connected. Complete graphs. A complete graph on n vertices denoted by Kn is a simple graph that contains exactly one edge between each pair of distinct vertices. The graphs Kn for n equal to 1, 2, 3, 4, 5, 6 are displayed. A simple graph for which there is at least one pair of distinct vertex not connected by an edge is called non-complete. Graphical representation. Carrying out graph algorithms using the representation of graphs by list of edges or by adjacency list can be cumbersome if there are many edges in the graph. To simplify computation, graphs can be represented using matrices. Two types of matrices commonly used to represent graphs will be presented here. One is based on the adjacency of vertices and the other is based on incidence of vertices and edges. Adjacency matrix. Suppose that G equal to V, E is a simple graph where modulus of V equal to n. Suppose that the vertices of G are listed arbitrarily as V1, V2, etc. Vn. The adjacency matrix A or AG of G with respect to this listing of the vertices is the n cross n 0 1 matrix with 1 as its I, jth entry when Va and Vj are adjacent and a 0 as its I, jth entry when they are not adjacent. In other words, if its adjacency matrix is A equal to Aij, then Aij equal to 1 if Vi, Vj is an edge of G. Aij equal to 0 otherwise. Use an adjacency matrix to represent the pseudo graph shown. Draw a graph with the adjacency matrix. The adjacency matrix of a simple graph is symmetric, that is Aij equal to Aj because both of these entries are 1 when Vi and Vj are adjacent and both are 0 otherwise. Furthermore, because a simple graph has no loops, each entry Aii, I equal to 1, 2, 3, etc. n is 0. Adjacency matrices can also be used to represent undirected graphs with loops and with multiple edges. A loop at the vertex Vi is represented by a 1 at the I, jth position of the adjacency matrix. When multiple edges connecting the same pair of vertices Vi and Vj or multiple loops at the same vertex are present, the adjacency matrix is no longer a 0-1 matrix because the I, jth entry of this matrix equals the number of edges that are associated to Vi, Vj. All undirected graphs including multigraphs and pseudographs have symmetric adjacency matrices. Use an adjacency matrix to represent the pseudograph shown. Another way to represent a graph is to use adjacency list, which specify the vertices that are adjacent to each vertex of the graph. Use an adjacency list to describe the simple graphs given. Table. See the figure as well as table where we highlighted. Anyone can understand easily. Use adjacency list to describe the simple graph given. You can easily see the figure as well as table where we highlighted. Anyone can understand easily. Incidence matrix. Another common way to represent graphs is to use incidence matrices. Matrix follows: V1, V2, V3, V4, V5 as rows, E1, E2, E3, E4, E5, E6 as columns. We can easily see the matrix using the figure. Let G equal to V, E be an undirected graph. Suppose that V1, V2, etc. Vn are the vertices and E1, E2, etc. Em are the edges of G, where Mij equal to 1 when edge Ej is incident with Vi, Mij equal to 0 otherwise. Represent the graph shown in figure below with an incidence matrix. So we can easily see the matrix using the figure. We clearly explained in the matrix where we have to see, where we have to catch the point. Euler path. The town of Königsberg, Prussia, now called Kaliningrad and part of the Russian Republic, was divided into 4 sections by the branches of the Prigel River. These 4 sections included the 2 regions on the banks of the Prigel, Kenipov Island, and the region between the 2 branches of Prigel in the 18th century, 7 bridges connected these regions. The town people took long walks through town on Sundays. They wondered whether it was possible to start at some location in the town, travel across all the bridges once without crossing any bridge twice, and return to the starting point. Euler path and circuit. Euler studied this problem using the multigraph obtained when the 4 regions are represented by vertices and the bridges by edges. This multigraph is also shown. First, Euler pointed out that the choice of route inside each land mass is irrelevant. The only important feature of a route is the sequence of bridges crossed. This allowed him to reformulate the problem in abstract terms, laying the foundations of graph theory, eliminating all features except the list of land masses and the bridges connecting them. In modern terms, one replaces each land mass with an abstract vertex or node and each bridge with an abstract connection, an edge, which only serves to record which pair of vertices, land masses, is connected by that bridge. The resulting mathematical structure is called a graph. Next, Euler observed that except at the endpoints of the walk, whenever one enters a vertex by a bridge, one leaves the vertex by a bridge. In other words, during a walk in the graph, the number of times one enters a non-terminal vertex equals the number of times one leaves it. Now, if every bridge has been traversed exactly once, it follows that for each land mass, except for the ones chosen for the start and finish, the number of bridges touching that land mass must be even. Half of them in the particular traversal will be traversed towards the land mass, the other half away from it. However, all 4 of the land masses in the original problem are touched by an odd number of bridges. One is touched by 5 bridges and each of the other 3 are touched by 3. Since at most 2 land masses can serve as the endpoints of a putative walk, the proposition of a walk traversing each bridge once leads to a contradiction. An Euler circuit in a graph G is a simple circuit containing every edge of G. An Euler path in G is a simple path containing every edge of G. The figure shows the concept of Euler's path and circuits. Which of the undirected graphs in figure have an Euler circuit? Of those that do not, which have an Euler path? Solution. The graph G1 has an Euler circuit. For example, A, E, C, D, E, B, A. Neither of the graphs G2 or G3 has an Euler circuit. The reader should verify this. However, G3 has an Euler path, namely A, C, D, E, B, D, A, B. G2 does not have an Euler path. Which of the directed graphs in figure have an Euler circuit? Of those that do not, which have an Euler path? Solution. The graph H2 has an Euler circuit. For example, A, G, C, B, G, E, D, F, A. Neither H1 nor H3 has an Euler circuit, as the reader should verify. H3 has an Euler path, namely C, A, B, C, D, B, but H1 does not. A connected multigraph with at least 2 vertices has an Euler circuit if and only if each of its vertices has even degree. An Euler circuit in a graph G is a simple circuit containing every edge of G. An Euler path in G is a simple path containing every edge of G. The graph shows the concept of Euler paths and circuits. Many puzzles ask you to draw a picture in a continuous motion without lifting a pencil so that no part of the picture is retracted. We can solve such puzzles using Euler's circuits and paths. For example, can Muhammad's scimitars shown in figure be drawn in this way where the drawing begins and ends at the same point? Solution. We can solve this problem because the graph G shown in figure has an Euler circuit. It has such a circuit because all of its vertices have even degree. First we form the circuit A, B, D, C, B, E, I, F, E, A. We obtain the subgraph H by deleting the edges in the circuit and all the vertices that become isolated when these edges are removed. Then we form the circuit D, G, H, J, I, H, K, G, F, D in H. After forming the circuit, we have used all edges in G. Splicing this new circuit into the first circuit at the appropriate place produces the Euler circuit A, B, D, G, H, J, I, H, K, G, F, D, C, B, E, I, F, E, A. This circuit gives a way to draw the scimitars without lifting the pencil or retracing part of the picture. A connected multigraph has an Euler path but not an Euler circuit if and only if it has exactly two vertices of odd degree. Which graph shown in figure have an Euler path? Solution: G1 contains exactly two vertices of odd degree, namely B and D. Hence it has an Euler path that must have B and D as its endpoints. One such Euler path is D, A, B, C, D, B. Similarly, G2 has exactly two vertices of odd degree, namely B and D. So it has an Euler path that must have B and D as endpoints. One such Euler path is B, A, G, F, E, D, C, G, B, C, F, D. G3 has no Euler path because it has 6 vertices of odd degree. Euler paths and circuits can be used to solve many practical problems. For example, many applications ask for a path or a circuit that traverses each street in a neighborhood, each road in a transportation network, each connection in a utility grid, or each link in a communications network exactly once. Finding an Euler path or circuit in the appropriate graph model can solve such problems. For example, if a postman can find an Euler path in the graph that represents the streets the postman needs to cover, this path produces a route that traverses each street of the route exactly once. If no Euler path exists, some streets will have to be traversed more than once. The problem of finding a circuit in a graph with the fewest edges that traverses every edge at least once is known as the Chinese postman problem in honor of Guan Meige, who posted it in 1962. Hamilton paths and circuits. A simple path in a graph G that passes through every vertex exactly once is called Hamilton path, and a simple circuit in a graph G that passes through each vertex exactly once is called a Hamilton circuit. That is, the simple path x0, x1, etc., xn minus 1, etc., xn in the graph G equal to V, E is a Hamilton path. If V equal to x0, x1, etc., xn minus 1, xn and xi equal to xj for 0 less than or equal to I less than j less than or equal to n, and the simple circuit x0, x1, etc., xn minus 1, xn, x0 with n greater than 0 is Hamilton circuit. If x0, x1, etc., xn minus 1, xn is a Hamilton path, which of the simple graphs in figure have a Hamilton circuit, or if not, a Hamilton path? Solution: G1 has Hamilton circuit A, B, C, D, E, A. There is no Hamilton circuit in G2. This can be seen by noting that any circuit containing every vertex must contain the edge A, B twice. But G2 does have a Hamilton path, namely A, B, C, D. G3 has neither a Hamilton circuit nor a Hamilton path because any path containing all vertices must contain one of the edges A, B, E, F, C, D more than once. Show that neither graph displayed in figure has a Hamilton circuit. Solution: there is no Hamilton circuit in G because G has a vertex of degree 1, namely E. Now consider H. Because the degrees of the vertices A, B, D and E are all of 2, Every edge incident with these vertices must be part of any Hamilton circuit. It is now easy to see that no Hamilton circuit can exist in H, for any Hamilton circuit would have to contain 4 edges incident with C, which is impossible. Applications of Hamilton circuits. Hamilton paths and circuits can be used to solve practical problems. For example, many applications ask for a path or circuit that visits each road intersection in a city, each place pipelines intersect in a utility grid, or each node in a communications network exactly once. The famous traveling salesperson problem, or TSP, also known in older literature as the traveling salesman problem, asks for the shortest route a traveling salesperson should take to visit a set of cities. This problem reduces to finding a Hamilton circuit in a complete graph such that the total weight of its edges is as small as possible. Traveling salesman problem. An important problem involving weighted graphs asks for a circuit of shortest total length that visits every vertex of a complete graph exactly once. This is the famous traveling salesperson problem, which asks for an order in which a salesperson should visit each of the cities on which route exactly once so that he travels the minimum total distance. Consider a 4-city TSP for which the cost between the city pairs are as shown in the figure. Find the tour of the salesperson so that the cost of travel is minimal. The traveling salesperson asks for the circuit of minimum total weight in a weighted, complete, undirected graph that visits each vertex exactly once and returns to its starting point. This is equivalent to asking for a Hamilton circuit with a minimum total weight in the complete graph, because each vertex is visited exactly once in the circuit. The most straightforward way to solve an instance of the traveling salesperson problem is to examine all possible Hamilton circuits and select one of minimum total length. How many circuits do we have to examine to solve the problem if there are n vertices in the graph? Once a starting point is chosen, there are n-1 factorial different Hamilton circuits to examine, because there are n-1 choices for the second vertex, n-2 choices for the third vertex, and so on. Because Hamilton circuit can be travelled in reverse order, we need only examine n-1 factorial by 2 circuits to find our answer. Note that n-1 factorial by 2 grows extremely rapidly. Trying to solve a traveling salesperson problem in this way when there are only a few dozen vertices is impractical. For example, with 25 vertices, a total of 24 factorial by 2 n-1 factorial divided by 2. 25 minus 1 factorial divided by 2 equal to 24 factorial by 2 equal to, we getting the answer, different Hamilton circuits would have to be considered. If it took just 1 nanosecond 10 to 9 seconds to examine each Hamilton circuit, a total of approximately 10 million years would be required to find a minimum length Hamilton circuit in this graph by exhaustive search techniques. Because the traveling salesperson problem has both practical and theoretical importance, a great deal of effort has been devoted to devising efficient algorithms that solve it. However, no algorithm with the polynomial worst case time complexity is known for solving this problem. Furthermore, if a polynomial worst case time complexity algorithm were discovered for the traveling salesperson problem, many other difficult problems would also be solvable using polynomial worst case time complexity algorithms. A practical approach to the traveling salesperson problem when there are many vertices to visit is to use an approximation algorithm. These are algorithms that do not necessarily produce the exact solution to the problem, but instead are guaranteed to produce a solution that is close to an exact solution. Brute force approach. List all of the possible Hamilton circuits. Calculate the total weights for each of the possible Hamilton circuit. Choose an optimal circuit, cheapest, shortest, or fastest. Start at C. C, A, B, D, C equal to 70 plus 20 plus 10 plus 50 equal to 150, that is 150. C, A, D, B, C equal to 70 plus 30 plus 10 plus 15 equal to 125, that is 125. C, B, A, D, C equal to 15 plus 20 plus 30 plus 50 equal to 115, that is 115. C, B, D, A, C equal to 125. C, D, A, B, C equal to 115. C, D, B, A, C equal to 150. Therefore, optimal circuits are CBADC or CDABC. If the problem asks to start at A, then the optimal circuits are D, C, B, A or A, B, C, D, A. Nearest neighbor problem. From the starting vertex, go to its nearest neighbor. The edge has the smallest weight. Repeating step 1 with the next vertex until there is no more vertex to visit. From the last vertex, return to the starting point. Start at C, pick CB equal to 15. From B, pick BD equal to 10. From D, pick DA equal to 30. No more vertex left, so connect A and C with AC equal to 70. Therefore, the route is CBDAC equal to 125. The brute force algorithm, optimal but inefficient algorithm. The nearest neighbor algorithm and repetitive nearest neighbor. Efficient but not optimal algorithms. The repetitive nearest neighbor algorithm. Apply the nearest neighbor algorithm to each of the vertices to calculate the total weights. Choose the best circuit. If there is a designated starting vertex, rewrite the circuit using that vertex as a reference point. Traveling salesperson problem. The repetitive nearest neighbor algorithm. Apply the nearest neighbor algorithm to each of the vertices to calculate the total weights. Choose the best circuit. If there is a designated starting vertex, rewrite the circuit using that vertex as a reference point. From A, B, D, C, A equal to 20 plus 10 plus 50 plus 70 equal to 150. B, D, A, C, B equal to 10 plus 30 plus 70 plus 15 equal to 125. C, B, D, A, C equal to 15 plus 10 plus 30 plus 70 equal to 125. D, B, C, A, D equal to 10 plus 15 plus 70 plus 30 equal to 125. One of the best routes is CBDAC equal to 125. Or if we rewrite the starting point A, C, B, D, A. Planar graphs. Consider the problem of joining 3 houses to each of 3 separate utilities as shown in the figure. Is it possible to join these houses and utilities so that none of the connections cross? This problem can be modeled using the complete bipartite graph K3.3. The original question can be rephrased as can K3.3 can be drawn in the plane so that no two of its edges cross. The graph is called planar if it can be drawn in the plane without any edges crossing, where a crossing of edges is the intersection of the lines or arcs representing them at a point other than their common end point. Such a drawing is called a planar representation of the graph. Is the graph shown in figure with the two edges crossing planar? The graph is planar because it can be redrawn without crossing as shown. Is the graph shown in figure planar? The graph is planar because it can be drawn without any edges crossing as shown. Trees. A connected graph that contains no simple circuits is called a tree. Trees were found as long ago as 1857 when the English mathematician Arthur Cayley used them to count certain types of chemical compounds. Since that time, trees have been employed to solve problems in a wide variety of disciplines. Trees are particularly useful in computer science where they are employed in a wide range of algorithms. For instance, trees are used to construct efficient algorithms for locating terms in a list. They can be used in algorithms such as Huffman coding that construct efficient codes, saving cost in data transmission and storage. Trees can be used to study games such as checkers and chess and help determine winning strategies for playing these games. Trees can be used to model procedures carried out using a sequence of decisions. Constructing these models can help determine the computational complexity of algorithms based on a sequence of decisions such as sorting algorithms. A tree is connected undirected graph with no simple circuits because a tree cannot have a simple circuit. A tree cannot contain multiple edges or loops. Therefore, any tree must be a simple graph. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. A rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. A tree with n vertices has n-1 edges. Spanning trees. Let a G be a simple graph. A spanning tree of G is a subgraph of G, that is a tree containing every vertex of G. Finding a spanning tree of the simple graph G shown. Find a spanning tree of the simple graph G shown. Finally, remove edge C, G to produce simple graph with no simple circuits. This subgraph is a spanning tree because it is a tree that contains every vertex of G. The sequence of edge removals used to produce the spanning tree is illustrated in figure. Cut set. A cut set is a minimal set of edges that, when broken, breaks the graph into two completely separate parts, two groups of nodes. Minimal means that a cut set cannot contain another smaller cut set that would break the graph into same two parts. Suppose I am given a tree. A fundamental cut set with respect to the tree is a cut set that only contains one branch of the tree. There may be fundamental cut sets with respect to a given tree. Finding fundamental cut sets. Redraw the graph with the tree in a straight line. For each tree edge, form its fundamental cut set as follows. That tree edge is a member of this fundamental cut set. Cut that edge. What two groups of nodes are separated? The fundamental cut set also contains all edges in the code tree that connect these two groups. Minimum cut problems arise in many contexts. Study of network reliability, smallest number of edges that can fail. Study of network optimization, find a maximum flow. Clustering problems, edges like associations, rules. Matching problems. The minimal spanning tree problem. Consider the undirected graph as shown in the figure. The graph consists of nodes and edges, and each edge has an associated length. An edge is the line segment connecting two nodes and has the same length in either direction. The minimal spanning tree problem is to select a set of edges so that there is a path between each node. The sum of the edge length is to be minimized. Minimum spanning. Sort the edges of G in increasing order by length. Keep a subgraph S of G initially empty for each edge E in sorted order. If the endpoints of E are disconnected in S, add E to S, return S. Prim's algorithm. Let T be a single vertex, while T has a fewer than n vertices. Find the smallest edge connecting T to GT, added it to T.